SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 25 and 26. We were discussing in the last module about binomial distribution, the way we calculate mean and standard deviation, and then we also tried to find out that how that can be related to the fraction defective or the fraction acceptable in a acceptance sampling plan. We are going to start today looking at some of the other kind of data bases which are available, and then trying to see if the binomial or some other distribution would work in that particular case. This right here shows 3 different tables, actually 6 different tables, where you have different situations recorded in terms of some value and a frequency. Let us say table A. So, table A is based on a 33 year of records for 10 rainfall stations. So, and this is widely scattered throughout the Midwestern United States, and it gives a minimum number of 10-minute periods in a year having half an inch or more of rainfall. C is the number of such cloud bursts in a station year, the frequency in years having respectively 0, 1, 2, 3, 4 and 5 such excessive rainstorms. So, here for example, this excessive rainstorm has been categorized to be a, let us say, 10-minute period in a particular year having half an inch or more of rainfall. So, these are basically, C is basically representative of how many such periods are available. So, you have 0 such periods, the frequency is about 102, you have 1 such period of 10 minutes or more having half an inch or more of rainfall. So, this is actually in terms of the number of stations which are present throughout the United States, the Midwestern United States, where this data has been taken, times of the years. Okay, so you have station years. So, in all these station years which are being in question, at least 102 station years have been recorded where there are 0 such cloud burst incidents, 114 station years have been recorded where there are 1 such cloud burst incident, 74 station years have been recorded where there are 2 such indications or 2 such cloud burst incidents, so on and so forth. And as the numbers go higher, you see 5 such incidents have been recorded in at least 2 station years. So, station years means the number of stations times the number of years. So, if it is a 1 year period, so it is typically the number of stations, or so on and so forth. So, the average number of storms per station year, C dash, is actually 1.2, which can be computed here by looking at the C times of the frequency. So, sigma Cf divided by sigma f, and that means on an average there are about 1.2 such cloud burst incidents of 10 minutes durations at least having half an inch or more of rainfall, which is recorded in almost all the stations in one particular year period, the Midwestern United States. That is what this data represents. A similar kind of data is represented here in table B, which shows deaths from kick of a horse, and you can see here that the table B here represents the number of cavaliers killed by fatal kick of horses in each of the 14 cavalry corps in each of the 20 successive years. Okay, so there is a time period which is there. There are 14 such cavalry corps which are used for recording such data, and then B represents the sort of number of cavaliers killed by the horse kicks which could be fatal, and this is a 20 successive years data. Just as in this particular case it was a 33 years data, so 33 times the number of stations would be really the total number of subject points which would be used in the case of excessive rainstorms. So, C here represents the number of Prussians which are killed in this way in a corps year. So, basically if you have 14 cavalries and you are monitoring all those 14 cavalries across 20 years period, if how many number of corps actually get killed by the horse kicks is recorded as C, and that shows that 0 such incidents of killing because of fatal kicks of horses occur 109 times. These times indicate the cavalry years. Okay, so therefore across all the 14 cavalries there are about 109 such occurrences in 20 successive years where there has been no death. There has been at least one death in 65 such 65 times among the 14 cavalries in the 20 successive years. Similarly, 2 deaths in at least repeated 22 times in the 14 cavalries for 20 successive years, so on and so forth, and that is how you have recorded this particular data. Okay. So what we are trying to see here is that the recording of this whole data is by taking into consideration at least 2 parameters which are about certain ranges. Like in the first case it was number of stations times number of years, and it is about 33 years across which all these number of stations have been monitored. So in fact the data size is large because of this, and you have made a abridged statement by saying station years, so that you can record all the frequencies in terms of the number of such incidents which are occurring. But in the case of deaths from kick of a horse, you are basically monitoring 14 cavalries across 20 years. So it is a large data set, but you are abridging that to a small table here and recording the number of deaths because of such cavalry years. So this in general is a way of representing or abridging a larger database by a smaller table. Okay. Similarly, you can have the table C of lost articles, which is based on the number of articles turned in per day to a lost and found bureau of a large office building. And the frequency is the number of days with exactly C lost articles turned in. So what it means is that if supposing there are a certain number of articles turned per day to a lost and found bureau, for a certain period of time, maybe let us say it is a month's time or a year's time, this has been recorded as exactly 0 articles are returned exactly 169 times across the whole number of such returns per day times the, or maybe the total numbers which are returned back. So at least 0 lost articles are turned in 169 times across the time period in which you are recording times the number of articles turned per day. Similarly, 1 for 134 times, 2 for 174 times, so on and so forth. Again a large data being recorded in an abridged manner. Table D, for example, shows the vacancies of the United States Supreme Court either by death or resignation of members from 1837 to 1932. So it records about close to 97 years or 95 years of subsequently so there are 0 such cases of vacancies coming in this United States Supreme Court either by death or resignation of the members at least 59 times among this 1837 to 1932 95 years period. Then there are at least one such case in about 27 times across this whole number of years, 97 years. Then about 2 such times in per year in a let us say at least 9 such cases, and then 3 per year obviously for about 1 case or so, where this is exactly the number of vacancies which are created on a yearly basis given this whole 97 year period. Again a very large data constricted into a small tabular form. Table E similarly shows the number of telephone calls per 5 minutes interval in a group of 6 coin box telephones in a large railway terminal. So the data were taken from for the period from noon to 2 p.m. for 7 days. The frequency number is the number of 5 minutes interval in which exactly C calls were made. So exactly 0 calls were made 8 times from the 6 coin box telephones for exactly 5 minutes per call kind of an interval, also for telephone calls made per 5 minutes interval, and such 8 such calls were there where the frequency were exactly 0 of the occurrence of telephone calls across this whole duration from 2 p.m. onwards in all the 6 telephone boxes. Similarly, the frequency number, so there are at least 13 numbers of at least 1 calls made from all the 6 boxes in the 5 minute interval, at least 20 numbers of 2 calls made from the 6 boxes on the per 5 minutes interval for a certain day from noon to 2 p.m. so on and so forth. So again a very large congregation of data being recorded here as a frequency table. So, the idea here is that in such cases there is very peculiar 2 or 3 characteristics of recording this data, and mostly all these cases are represented by a certain distribution, just as the binomial distribution was earlier well discussed in the case of acceptance sampling by something called a Poisson's distribution. So, the 6 Poisson illustrations may seem to have very little similarity to one another, but I will just record in this few statements what are the kind of similarities which will be there. So, let us look at them more critically, all the 5 illustrations, for example, the rainfall problem, the the fatal kicks problem, the number of telephone calls problem, the number of seats in the Supreme Court and number of vacancies in the United States Supreme Courts, that problem, or the number of lost articles returned back to a building problem. So, they all have definite characteristics in common. In each, a count was made of the number of occurrences of an event that had many opportunities to occur, but was extremely unlikely to occur at any given opportunity. That is why the very large database which is in question. Okay. So, at least something is common in the data structure, that in each a count was made of the number of occurrences again of an event that had many opportunities to occur, but was extremely unlikely to occur at any given opportunity. For example, there were 10 minutes period in a year. It was unlikely that any particular one would bring a cloudburst of half an inch or more of rain. Similarly, there were many contacts between cavalryman and horse during a year of history of a cavalry corps. It was unlikely that the horse would make of a fatal kick at any particular contact. Similarly, there were many people passing through the office building throughout the day. It was highly unlikely that any one person would find a lost article and turn it into the lost and found section. So, all of them are very unlikely to occur, and their probability of occurrence is quite low. So, Poisson's distribution is generally applied to such a kind of data set where the probability of occurrence of an event is quite low, and you need really an extensively large database to somehow make the probability quite realistic. So, in all these cases there is a concept of existence of large n, that means the overall sample size that you are examining or the data structure you are examining is a very high value and a very small probability of occurrence in that. So, the p is very small, even though it may be impossible to assign a definitive value to either n or p. Even in cases where it is not impossible to assign a definite value to either n or p, it may simply be of no advantage to determine n and p and to calculate the binomial based on them. So, this is a case where your n and p are so bizarre that the n is on the higher side and p is on the extreme low side, that you do not have really an upper limit of the largeness of the data size that is needed, so that the probability, even if it is very small, can come into some realistic value and it can be at least recorded as occurrences of the event. Otherwise, the events are extremely unlikely in nature. So, in such cases Poisson's distribution is definitely an advantage over and above the binomial cases. Binomial cases is a straightforward case where the acceptance percentage or the probability of a sample to be good or bad is quite reasonably high number. 10% in fact what we took in the binomial distribution is a very high number. Here this data structure, particularly if the acceptance rate is higher, can be a little bit lower also, but still you can have good accuracy to predict, etc. But in cases when this p is extremely slow and the event is highly unlikely to occur, obviously the data structure would increase. Okay. So, let us now look at the characteristic property of what is the Poisson's distribution. So, let us say if C is the count of occurrences of some event of interest and mu C is the parametric value of the rate of occurrence, then the Poisson's probability density function may be stated as simply probability of count of occurrences C with the probability of, let us say, mean probability of mu C occurrence can be represented by mu C to the power of C by factorial C e to the power of minus mu C, and as such the cumulative distribution function in such a case as the probability of R to be less than equal to C given a certain occurrence rate of this particular count of occurrences can be represented as sigma R varying between 0 to C mu C to the power of R divided by factorial R e to the power of minus mu C. So, that is how you mention the formulation the Poisson's formulation for calculation sake. I am going to derive this out from the condition that had been just illustrated earlier, that what is the difference between binomial in this particular case. So, calculation involving the use of binomials are often burdensome. This is particularly true if many terms are involved and if n is particularly large, as in the case of the distributions that you have been seeing where the occurrences are highly unlikely. Okay. Fortunately, a simple approximation may be obtained to any term of the binomial, and this approximation is also called Poisson's exponential binomial limit. The larger the value of n, the smaller the value of p, the closer the Poisson's approximation. And the Poisson formula may be derived from the binomial theorem in the following manner. So, let us say if I look at the chances of occurrences of an event for a certain, let us say number of chances of occurrences R, the probability of that occurrence can be provided by the binomial term n factorial by R factorial n minus R factorial times of the probability of occurrence of the event to the power R plus probability of the event not occurring to the power of n minus R. So, if I wanted to simply substitute the Cp equal to n, C equal to Np in this particular expression, obviously the p is very small and n is very large, as the cases that you have discussed before. So, this expression can be again written as factorial n by factorial R times of factorial n minus R, and value of p which is C by n to the power of R, and 1 minus C by n to the power of n minus R. Okay. So, I can again do some algebraic manipulation here by recording this as the factorial n by factorial n minus R factorial R, and what I can probably do is that we will just swipe over. So, this can come from the next term. So, this is n to the power of R, and the C to the power of R can be divided by factorial R. So, basically I am just taking this term and putting it here in the interest of just simplifying the expression. Okay. And then we have obviously 1 minus C by n to the power of n and times of 1 minus C by n to the power of minus R. So, at this stage the limit of each term is taken, allowing n to go to infinity, because obviously the n in the Poisson's distribution, as you know, is very large, and holding the C equal to Np as constant. So, obviously you can find out that the chances of occurrence are really dependent on these two values, and the probability is very low, highly unlikely, and that is why n goes to infinity. So, you can have the number of occurrences of a particular kind. So, let us just put this limit here and see what happens to this expression. So, the limit of n going to infinity factorial n by factorial n minus R times of n to the power of R, if n is very high, is actually equal to 1 for obvious reasons, because n being very high is also very higher in comparison to R, and so you are basically left with n factorial over n factorial, because the R being much smaller, even the n to the power of R will not have significant contribution in this particular case actually. So, the other issue is the limit of n going to infinity C to the power of R by factorial R. So, this value is independent of n. So, it would as such remain C to the power R by factorial R. The other term if n is limited to infinity is 1 minus c by n to the power of n, so which can be recorded as 1 minus nc1 c by n plus nc2 c by n square minus nc3 c by n cube plus so on and so forth, and the limit of n tends to infinity of this particular expression where n is very large actually. So, in fact, this turns out to be e to the power of minus c, where the value of e is 2.71828. Similarly, for limit n tending to infinity, 1 minus c by n to the power of minus r is actually recorded as 1, okay, because n being infinity, this part would obviously be 0, and therefore, the r value being small, this can be recorded as only 1. So, I am not really going to delve into the process of proving how this limit comes out, because it is actually understood to have been done at a different course module earlier, covered earlier. But if there are any questions regarding this, and if you have any single query, you could send, and then if need be, this proof can be sent online later on. So, the basic idea is that with all these limits on board, as n increases, without any bound, the limiting case of the binomial distribution stated as the probability of r occurrences given a large sample size n and the probability of one occurrence as p small is actually given by NCR p to the power of r 1 minus p to the power of n minus r, and this becomes actually equal to, in this particular case, the limit at n equal to infinity of n by n minus r factorial n to the power of r, which is 1, times of c to the power of r by r factorial times of e to the power of minus c times of 1. Okay. So, that is what is the limiting case of the Poisson's distribution, which says that p of exactly c occurrences given a certain rate at which the occurrence is happening is given as mu c to the power of c factorial c e to the power of minus mu c. Okay. So, this is nothing but initially saying that the c can be recorded as np in the expression given earlier here, and certainly this can be changed to 1 times of np to the power of r by factorial r e to the power of minus np. So, np, as you know, in the binomial distribution, if the n were significantly large and p is significantly small, is basically the mu of the distribution, mu of r, and r being np is basically again this occurrence level c, particularly in this particular case, which is actually giving out this Poisson's distribution. So, the expected number of occurrences obviously are probabilistically determined by mu c to the power of c factorial c to the power of minus mu c. So, the standard tables provide summation terms of Poisson's cumulative density function up to 3 decimal places. I will share these tables when we do some numerical examples later on. Individual Poisson's terms must be obtained by subtracting terms of the adjacent summation series. So, thus any particular let us say probability function of c occurrences given the mean occurrence level as mu c is actually given by the cumulative density function of any r less than c given mu c minus probability density function of any r less than or equal to c minus 1 given the mu c term. The average and standard of the Poissons can also be calculated. So, the average and the Poissons distribution are basically average and the standard deviation of the Poissons distribution are, as you saw earlier, mu c is actually mu of np, and in fact the root of mu c can also be represented as root of mu np. For the same reason, mu np from the binomial distribution was represented as np, and sigma np from the binomial distribution was represented as np times of 1 minus p. I had made detailed proofs in the earlier binomial distribution case. In case of binomial distribution, in this particular case it is a limiting case where EC is equal to NP, E of NP. So, obviously the mean in the Poisson's distribution then would be the mathematical expectation of NP, which is the mathematical expectation in the binomial terms is again the value NP. So, if the occurrence is very large here, C is NP, so it basically becomes C. Okay, so that is the mean of the binomial distribution, and the sigma of the binomial distribution in this particular case being NP times 1 minus P can be represented as C times 1 by C, 1 minus C by N whole under the root, or in other words you can represent this as root of C as the size of the N is very large. Okay. So, the mean of the binomial distribution is the number of occurrence C, and the standard deviation the Poisson's distribution, and the standard deviation of occurrence of the particular distribution, Poisson's distribution, for a very large sample size and limited to infinity, which is actually the case when you are applying the Poisson's distribution is root of C. So, that is about it. So, you have seen the binomial, you have also seen cases where the occurrences are very highly unlikely and there is a huge database. So, that is represented by the Poisson's distribution. This particular module will close here in the interest of time, but in the next module we would like to see again another case of another distribution called the normal distribution, which can be later on very easily applied, particularly to some of the acceptance sampling problems where the distribution slightly changes than what you saw in the acceptance sampling case earlier where binomial was applied. So, thank you as of now.